Guys, hello everyone and welcome to the channel and welcome to another video on 10 challenging question series. In this series we are taking 10 new questions, 10 challenging questions which are different from what they are asked in the previous CSIR NET exam. And these questions are I am going to take these questions from my ebook which I have recently launched, which contains more than 1000 questions on different topics of chemistry. And in that ebook also you will find topic wise questions, means the questions are there in topic wise manner. There are new questions over there with detailed explanation. So I am going to take 10 challenging questions from my ebook. Those are going to be 10 new questions on stereochemistry. So today's topic is going to be stereochemistry, because in the previous video many of you have asked to make video on stereochemistry. That's why I'm going to take this. And what topic you want me to cover in the next video, to let me know in the comment section as well. So here in this video, as we have done the previous one, in the previous video we did organic spectroscopy. In case if you have not watched that, I'll give you link of that in the I button. So in that video also, we have taken 10 new questions and we have seen how to solve them. In the similar manner we will take over here as well. So stereochemistry is a very typical topic. The questions are going to be asked based upon R and S nomenclature, based upon helical compounds, planar chirality. So all these type of questions are covered in this particular video. So do watch till end and try to understand what is the concept behind it. And that's all about it. So now let's continue with the video. Okay, so this is the first question. It says that the absolute configuration of the following compound is. So the compound is given to you and the options are like M minus, S, R or P plus. So basically this particular type of molecules where there are 3 fused rings and these are all like aromatic rings. So in this case the compound has a chirality due to helix, okay, or called as helical chirality. Okay, so the compound has helical chirality. Now if the compound has helical chirality, the naming of that compound is done either M or P. Okay, so P is done for if your rotation is clockwise rotation. Okay, so if your rotation is clockwise, in that case we call it as P nomenclature, and for M we for anti-clockwise we have so we have M nomenclature, right? Now from where you have to start your rotation. So if you look upon this dark side is the one which is towards you or which is above side. Okay, so this is a helical molecule, just like a spiral it is going. So it is, you have to start it from the group which is above the plane or which is shaded dark. You have to start from there. Okay, so if I start from here and if I make the helix, so it goes in this manner, and if you see, this is nothing but a clockwise direction. Okay, so this is a clockwise rotation for this given molecule. Because it is a clockwise rotation, its name should be, or its configuration should be P plus. Okay, so that's how we do the configuration for helical molecules. It is as simple as that. Previously CSIR has asked questions on this once or twice, and if they will ask this type of question, they will ask it in 2 marker. You should be careful with M and P nomenclature. You have to start numbering from the group which is above the plane or which is shaded dark, and from there you have to go to the group which is not shaded dark or the one which is shaded light. And in that case, if it is going clockwise, then P. If it is going anti-clockwise, in that case M. Alright, now let's take the next question. Right, so let's take this question. Here it says that identify the correct option about the absolute configuration of the following compound and the reason for its chirality. Now this is a particular type of molecule. Now one thing which you have to understand about these type of molecules, they are quite special type of molecules. They are called as paracyclophanes. Okay, so they are called as paracyclophanes, and they have a special type of chirality. See, there are various type of chirality: chirality due to chiral point or chirality due to chiral axis. Here the chirality is due to planar. This is called as a planar chirality or chirality due to a plane. Okay, So what happens actually, that this benzene ring is planar benzene ring, okay, it's on the plane, whereas this, the second benzene ring, is out of plane, okay. So this is not on in the plane itself. See, it is shown with this wedge also, that dark side, that it is towards you and the other side will be out of you. So one of the benzene is like this on the screen, and the other benzene ring is like this. So that's why they gain a chirality, and that is called chirality due to a plane, or also called as planar chirality. Okay, so planar chirality. Now in this case, they don't have axial chirality, they have planar chirality. So that's why you can cancel out option B and option C. Now among option A and D, you have to now look upon pilot atom. So pilot atom means the group which is out of plane, the one which is not in the plane. You have to see that particular group, and you have to start numbering over there from the this particular substituent. Okay, so the numbering for this one will be done in this way. So I'll just do it. So this will be called as first, second, third and fourth. So this, because this ring is the this ring is going to be given more priority, this atom will be called as the pilot atom, and from here the numbering will start, and this is how we are going to do it. Goes in the if you see, it goes in the anti-clockwise direction, right? So if it goes in the anti-clockwise direction, it has S configuration. So that's why your correct answer becomes option number A. Okay, so two things about this type of molecule: they have planar chirality, they have two types of ring, one on the plane and one out of the plane. You have to like give configuration from out of the plane group, and you have to start your numbering from the pilot atom. Pilot atom is nothing but the atom which is joining the two rings. Okay, so the para position, the atom which is joined over here, you have to start numbering from there, and this is how the numbering will go. And then you have to see that whether it is going clockwise or anti-clockwise, depending upon that. If it is clockwise, in that case it is R. If it is anti-clockwise, in that case it is S configuration. So that's how option number A becomes correct choice for that. Let's take the another question. Alright, now this is quite simpler question. It says that the configuration of the three asymmetric carbon center in the following compounds are. Now I will suggest you to pause this video and to solve this of your own, okay? Because this type of molecules are where people do a lot of mistakes, because they look very simple, but still you have to be very careful while solving these type of question. So here you have three chiral centers, chiral center 1, 2 and 3. They have mentioned like this. What you have to do first of all is write down them separately. Okay, so if I just quickly change the color of my pen. So yeah, so now if I talk about chiral center number 1, so chiral center number 1 has groups like this. Okay, so this is chiral center number 1. Now if I give priority, so this side will be given as priority, first priority. So I'll write down first priority on the right side. This side will be given second priority. Now why is this side given second priority? You have to understand. See, this side it is one carbon attached to oxygen and carbon. This side it is one carbon attached to two carbons. Since oxygen is more heavier, that's why I am giving more priority to this. Okay, this is given second priority because now the carbon is attached to two carbon, which is the second heaviest side. Now this side, this is going to be the third priority group, because here the carbon is attached to just one carbon and two hydrogen. So that's why this is the third priority group, and this is the fourth priority group. Okay, now whenever you have something like this, don't just start numbering your, or don't just start forming the configuration. The first rule or the first way how to achieve to the absolute configuration in an easier way is that you have to bring this fourth like priority group to this position, to the downside. Okay, in that case you will always get the correct answer, and for that you can do even number of changes. You can do changes to the group in the adjacent position, but remember, you have to always do even changes. If you do odd changes, configuration is going to get reversed. I hope you all know about these things. If you don't know about them, I have made a detailed video on it. I'll give you a link of that. You can watch over there. Okay, so I am going to do the first change. I am going to just exchange these groups. So it is going to become something like this. 1 will come here, 4 will come here, 3 is there itself, 2 is there itself. Now I will again do one more change, because I have to do even changes, right? So second change, is I'm going to change these two groups. So now now the groups will be like this. So 4 will come this side, 2 will come this side, 1 will remain here, and 3 will remain here. Now you can do the configuration of this. Now you can find out the configuration. So if you see the configuration, it goes like this, right? It goes clockwise. So first is R, okay? So the first chiral center is having R as the configuration. Now in that case, you can simply cancel out option number A, right? Option A can be simply cancelled out. Now you have to go for chiral center number 2, which is this one. So when I talk about chiral center number 2, let me erase the previous one because that's what is going to make difference. Okay, so on the chiral center number 2, I again have to give the priority. So on this side, I have oxygen, which will obviously given first priority. So this is the first priority group. On this side, I have carbon attached to 3 other carbons. So that's why this is going to be the second priority. Then this side, I have carbon attached to 2 hydrogen and a carbon. So this is the third priority. And since fourth group is not there, so I can keep the fourth group over here. Now, here automatically I have fourth group on this position. So that means I don't have to do any even change or anything. I have my group over here. So now I can directly find out the configuration. So if I see this goes in anti-clockwise direction, right? So if it is going in anti-clockwise direction, so I can say that the second chiral center has S configuration. Let's talk about the third chiral center. Now over here, if you see the first priority group will obviously this side because here is a carbon attached to 3 different carbons. Then the second priority group will be this side because here if you see the ring on both the side is similar, just over here you have oxygen also, but this side there is no oxygen, so that's why this is the second priority, this is the third priority. Now if I draw it on this Fisher diagram, in that case first will be here, second will be here, third is over here, and fourth is here. Again, I don't have to do anything, I just have to see the rotation, and since the rotation is clockwise, that's why it is going to give you R. The previous one was S. So my third chiral center is going to give me R. So R, S and R, that is my answer, and that's why option number B is going to become correct choice for this. All right. So it is very important to look upon the priorities and to find out the configuration of this, right? I'll just give you a quick question so that you all can also try it. Okay, so just try it out and tell me that what will be the absolute configuration of the chiral center. Okay, so this is going to be the first chiral center and this is going to be the second chiral center. Tell me the configuration of chiral center number 1 and chiral center number 2. Okay, this is a homework question for you all. All right, let's take the next question. All right, the question says that the relationship between the isomer in the image 1 and the isomer in the image 2 is, okay. So see, in order to do these type of question, you have to look upon their absolute configuration when you have more than one chiral center in both the molecules. Remember that if you have, let's say, a minimum 2 chiral centers in a molecule, and if you are getting R and R for one, and if for the other also you are getting R and R, in that case they will be called as identical. Okay, if let's say one is R and R and the other one is R and S, in that case they are diisomers, right? But if let's say you are getting R and R and for the other you are getting S and S, that means absolute opposite configuration, in that case they will be called as enantiomers. So now let's try to look upon these molecules and see what is the configuration in the chiral centers of these. So I have just zoomed it up a little bit. Let's look upon this particular center as the first center. Over here the first priority group is of course this OH group. The second priority group will be this side because here you have carbon and then oxygen. Here also you have carbon and oxygen but with a single bond. So that's why this is the third priority group. And this is the fourth priority group. Since fourth priority group is below the plane, you don't have to change the configuration at all. Just you have to see the rotation. If it is going anti-clockwise, so that means it should be S. Okay, so if it is S, it will remain S. So for this group, we have found configuration to be S. Similarly, we will try to look for this particular chiral center and let's try to find out the configuration for this. Again, this OH side will be given first priority. The second priority over here, see here you have carbon attached to oxygen and hydrogen. here again carbon attached to oxygen and hydrogen, but this side you have carbon attached to oxygen with a single bond, this side you have carbon attached to oxygen with a double bond. So this side will be given more priority. So that's why this is going to be the second number, this will be the third number, and this is the fourth number. Again, since the fourth priority group is below the plane, you don't have to change the configuration, you just have to see the rotation. It's going clockwise, so that's why this is R. Okay, in the same way you have to find out for this particular chiral center as well. So again, this is going to be, okay, let me change the color. So yeah, this is going to be first priority group. This okay, now this side you have carbon attached to oxygen, attached to hydrogen, and attached to a carbon. This side you have carbon attached to oxygen and two hydrogen. So that's why this should be given second priority, this will be given third priority, this will be given fourth priority. So the rotation goes anti-clockwise, but because the fourth priority group is above the plane, that's why you have to reverse the configuration. Although it was going anti-clockwise, it should be S, but because the fourth priority group is above the plane, that's why this will also become R. So what we have got? We have got R, R and S as the configuration over here. Okay. Now let's try to look for this particular molecule. Now understand that whatever this, whatever this particular chiral center is, let's call this as chiral center number 1, this as chiral center number 2, and this as chiral center number 3. So we have got 1R, 2R and 3S, right? Now here the number will be reverse. See, this is OH, so this is OH. So this is our first chiral center, this is the second chiral center, and this is the third chiral center. If you try to find out the configuration of them, I'll give you as a homework to do that. I'll directly tell you that what you are going to get. So in this molecule you will get 1R, you will get 2 as S, and you will get 3 also as S. Okay, now if you see, it's like if you just look upon both the molecules, so here first is R, here also it is R, here second is R, it became S, here third is S, it remained S. So it looks like this is going to be it looks like they could have been identical if this would have been R in this case, right? But they are not identical, they are not enantiomers, they are not mesodiastereomers, but they are none of the above. Okay, they are none of these. All right, so this is how it has to be done. You have to look for absolute configuration, and with respect to that you have to look. And it was very important to look upon the groups, like how you have numbered them. If you would have not have numbered them properly, you would have ended it like R, R, S, and this would have S, S and R, and you would have said that these are enantiomers. But it's not like that. You have to see that which chiral center you are giving the absolute configuration. All right. Okay, let's take the next question. All right, let's take this question. It says that the correct relationship between the following compound is. Now this is a trick question. These two molecules look very different from each other, but you have to do something in order to get it. Okay, so there are options like enantiomers, homomers, diastereomers, regioisomers. I have made a dedicated video on this where I have explained how to find out homomers, enantiomers, diastereomers. Okay, how to find out two hydrogens are enantiomers or diastereomers. So I'll recommend you to watch that video. I'll give you link in the I button. You have to watch that in order to understand it in more detail. But here I'll just tell you quickly. See, if you rotate some molecule by any axis of rotation, you don't change the configuration of it, it remains same. Okay, if it is it forms homomers. If the two molecules are interchangeable by some axis, in that case nothing is going to change in the molecule. So what I am going to do right now is, in this molecule A, I am going to apply a C2 axis. Now you have to imagine this C2, it is passing in between of these two carbon atoms, and it is passing like this. Okay, if I rotate it, what I am going to get, see, my molecule is now going to become something like this. Yeah, so this D which was on this side is going to go on this side, and this D which was on the back side is going to come on this front side. Oh sorry, because we are doing a rotation by 180 degree, right? C2. So this D will go on the opposite direction, which is just opposite of this. So it will go on this side. All right, so this is how it is going to look. Now you can see these two molecules look very familiar with each other. This particular molecule, if you apply a plane of symmetry, you are going to end up getting this one, right? So that means Okay, let me draw. This is molecule A itself. Okay, because you have just rotated it, nothing is going to change in the molecule A, and the molecule B is like something like this. All right, so yeah, this is something like this. Now if you see both these molecules, they are exactly same, just they are mirror images of each other. So if I apply a mirror in between them, in that case I will get it. And you know, if two molecules are mirror images of each other, they are called as enantiomers. So why this was trick question? Because they have given this A molecule in a different orientation. In order to see the correct orientation of it, you have to rotate it by C2 axis to get the correct relationship between it. If you will not rotate it, if you will directly see, it looks like they are diastereomers or something different. Okay, so you won't be able to find out. But yeah, this is how it needs to be done. I hope you understood. Let's go to the next question now. All right, let's look upon this question. It says that select the most stable conformation for structure 1 and least stable conformation for structure 2. If you look upon the molecule over here, before going into it, you need to know few basic things. Okay, so like when you convert this planar structure into the chair form, so there some rules we have to apply. Those rules says that if the substitution is on 1 2 or 1 4, okay, and if they are cis to each other, in that case it has to be axial equatorial, means one group will go on the axial position, the other group is going to go on the equatorial position. Then if you have 1 2, means 1 2 substitution or 1 4 substitution, okay, first and fourth position substitution, and if they are trans, in that case they can be either axial or equatorial. They can be anything. Okay, so either axial or equatorial. Now for 1 3 the rule reverses out, but because we don't have a 1 3 substitution, or you can write it down like if you have 1 3 cis, in that case they can be either axial or equatorial, and if you have 1 3 trans, in that case they will be axial equatorial. So this is the this is how we convert planar structures into chair form. So for the first one, we have to look for most stable conformation. So if you look the molecule first, like this is first position, this is second, this is third, and this is fourth. So if you see, this is the case where 1 2 trans is there, right? 1 2 trans, it should be either axial or equatorial. So let's draw both the conditions. Okay, so this is our chair form. 1 2 trans means either we can draw these methyl group like this, or we can draw them like this. All right, so I am just drawing the first one. So equatorial, so like this. All right, now this fourth group, if I see with respect to first, it is 1 4 cis. Now I told ki if it is 1 4 cis, it has to be axial equatorial. So if this methyl is already axial, the fourth one has to go in the equatorial position. That means the tertiary butyl group has to go over here like this. But in this case, because we have to make 1 4 cis and we have to make it axial equatorial, one group is already equatorial, so the fourth group will go axial with respect to that. So here tertiary butyl group will go axial to that. Now tell me which is more stable one. Tertiary butyl is a very bulky group, and if the bulky group stays on the equatorial position, it is more stable configuration, right? Although here methyl groups are on the axial position, you might think that this is going to make the molecule less stable, but we have to look for the stability with respect to most bulkiest group, which is tertiary butyl in this case, and that's why this configuration is the correct most configuration. Okay, this is the most stable conformation for the first one. Similarly, if we go for the second molecule, and let me change the color of my pen. So now if I have, this is 1 and 2. Now 1 2 cis. Now 1 2 cis, I told you again that that it has to be like either axial equatorial. Okay, it can be axial or equatorial. So let me draw it like this. So it has to be like methyl, one methyl on the axial position, the other methyl on the equatorial position, and then 3 and 4 we have 1 4 trans. 1 4 trans has to be either axial or equatorial. Now because this one position, this is 1, 2, 3 and 4. So since on the first position I already have axial group, so this fourth position group also has to go on the axial, then only axial will get satisfied, right? Because 1, 4 trans we have, so it has to follow axial or equatorial. Now because on the first I don't have equatorial thing, so that's why I have to make it axial itself. So this tertiary butyl goes something like this. Now this is a very less stable group, because tertiary butyl group being very bulky is actually going on the axial position, which is less stable. So this is the less stable configuration, but then also that was they were asking, right? So both these are the correct answers, and that's why these are basically given in option number C. Now you might ask what is the correct or what is the most stable conformation for the second one. So let me show you that also. If I draw the chair form again, and if I draw on the first position, if I draw this methyl group, on the second position I told you that they have to be axial equatorial. Here I draw on the first axial, on the second equatorial. It could be like this also, right? Like equatorial and axial, right? Now again I told for 1, 4 they have to be either axial or equatorial. Now since I already have on the first position I already have equatorial, so the fourth one has to be equatorial in order to satisfy the trans position. So that's why my tertiary butyl group will come over here. So this is going to be the most stable conformation for the second one, which is not given like in any of the option, I guess. Yeah. So yeah, according to the question, most stable conformation of first is here and the least stable conformation of the second is here, and that's why option number C is the correct option for this. All right. So I hope this is clear to you. Let's take the next question now. All right, let's look upon this particular question. Over here it says that consider the given statements regarding the given molecule. Okay. Statement 1 says that rate of racemization of A is more than that of B. Then second says rate of racemization of B is more than that of A. Third says absolute configuration of both compound is R. Fourth says absolute configuration of both compound is S. Now these are the molecule which are chiral because of chiral axis, because of the presence of chiral axis. And in these type of molecule, in order to make or in order to name them R and S, there is a rule. Now see, you will find out these are biphenyl groups. One phenyl ring is on the plane and one phenyl ring is out of the plane. The phenyl ring which is on the plane should be given more priority, and you have to start numbering, like you have to consider this line as the groups, and you like this line as the axis, and then you have to number the group on each side of it. Okay. Of course, this side you have nitrogen attached to, this will be given number 1, and this side you have carbon attached to, this will be given number 2. We have to always start numbering from the phenyl which is on the plane. Now you can number the other phenyl which is out of the plane. So here this will be given the third number. Why? Because this side you have oxygen, and this will be given the fourth number because this is like this, right? So this is how the numbering will be done over here. Again, if you go to this molecule and if you see the numbering over here, so first number to this side, second number to this side, this on the other side, if you see, again the the third number will be here because this is attached to oxygen, and here it is not attached to anything, but after the other carbon is attached to nitrogen. So this will be given less priority than that. So fourth priority over here. So the priority of the groups is similar in both the cases. So now you have to look for the rotation. Whenever you try to draw the rotation, you have to see that you have to make an arrow. Okay, arrow in the direction of the ring which is out of the plane. Now draw it like this. Okay, towards the right side of this arrow you have 2, so write down 2 here. Towards the left side of this arrow you have 1, so write down 1 here. This 4 is 2, like this is on the side which is towards you, or which is on the wedge side, which is dark shaded. So when this side which is dark shaded, that is given fourth priority. Dark shaded group is above side or towards the top. Okay, so this is fourth and this is 3. Okay, so this is for compound number A. Similarly, the similar numbering will be done, of course, for this as well. For compound number B also we will be having similar numbering. So we will be having 1 on the left side of this arrow and 2 on the right side of this arrow. Okay, how I am seeing left and right? Just see the arrow. You can rotate the mobile or laptop, whatever you are watching, just rotate it and you will see that this 1 is on the left hand side of this arrow and 2 is on the right hand side of this arrow. This is how it is. Then 4th, because it is on the wedge or the dark side, that's why it is above, and 3 will be downside. Now when you start rotating or rotation, I already told you previously that this 4th priority group should come in the downside, or if it is staying on the on this like vertical line, then also it's okay, you don't have to do the changes. But in case if you want to make it clear, or in case if you have just remembered one concept, you can make even number of changes in this, okay, although it is not going to change the configuration, but still if you want you can do that. I personally like to place the 4th priority group over here always, so that's why I'm doing it. It's up to you. If you don't feel like doing it, so you can avoid it, okay, you can directly do it because 4th priority group is already on the vertical plane. So this is one time change I have done. Second time when I'll do the change, I will replace these two groups and my 4th priority group will come here, 3rd will come here, 1st is already here, 2 is here. Now if you see the rotation, it is going like this, right? It is going in the clockwise direction, so that's why it will be R, okay. So this is R, and similar, because both of them have same numbering, so this is also R and this is also R. So the absolute configuration of both the compounds is R. So statement number 3 is correct. So you can cancel out option A and you can cancel out option C. So statement 3 is correct. Now you have to see that where racemization is going to be more, okay. So for that you have to remember one concept. In order to understand the racemization part, that is statement 1 and 2, where the rate of racemization is asked, you have to look upon the ring where the rotation is more restricted, where the rotation is not going to be possible, okay. So if the ring is not rotating, if this rotation along this sigma bond is restricted, in that case racemization of that particular group is going to be more, right? So rate of racemization of that will be more. So that's how we have to understand. So for that there is an effect called as buttressing effect, okay. So I hope you have studied this already. If not, please do study about this. It's a very small effect. What does this effect say is that if there are two rings, okay, so if let's say that I have a biphenyl ring molecule, something like this, in which the rings rotation of the ring is restricted, okay, let's say this is a biphenyl group, and I have some alkyl group which is at the ortho position, just to restrict the rotation of them. Now in that case, if let's say I have, or to be very precise, let me draw it like this. So if I have the alkyl group like this, in order to restrict the rotation, so now these phenyl rings can actually rotate if these like alkyl groups are going to bend away. If they bend a little bit away, they can rotate, but that bending of these groups or bending of these bond can be restricted further if I place a group at this particular ortho position. So if I place a group at the ortho position over here, that is going to restrict the bending of these R groups away, and that's why they are not going to rotate now, and that's why racemization will be more over there, or rate of racemization will be more. So this effect is called buttressing effect, which prevents the rotation of these biphenyl rings. And if you see both these molecules, this thing is possible in A only, because here again the rotation would have been possible if these groups move away from each other or these bonds actually bend away, but because of the presence of this nitro group, it's going to cause, or it's going to restrict that particular bending, and that's why A will give you more racemic mixture, or it will be formed as more of, you know, two enantiomers over there, or two configurations, whereas in B the rotation is possible, and that's why the less number of different configurations will be there. They can rotate and they can be converted in each other. That's why rate of racemization will be more in option number A, and that's why statement number 1 becomes your correct choice, and that's why correct answer becomes option number D, which says statement 1 and statement 3 both are correct statements. So this buttressing effect, sometimes also called as BE effect, please do read about it if you have not studied yet. All right, if you have studied this already, please do let me know in the comment sections below. All right, let's take the next question now. All right, so in this question, a very important concept is going to be discussed, stability of alkenes, which we generally ignore. but here it says that the correct increasing order of the stability of the following conformation of 1-butene is. Now see, in butene or propene, in all these alkenes, we have two types of conformations. Like in alkanes, we have a eclipsed and staggered conformation. Over here, we have eclipsed and bisected conformation. Those you will be able to understand if you draw Newman kind of projection for this. So let me draw for all these molecule. So for the first molecule, I can draw the backside carbon like this. Okay, CH2, and then I have H. And if I try to draw for this carbon, this will go like this. Okay, so I will make it like, okay, so let me change the color so that you understand. So yeah, so this side is going to have CH3 and then I have H. Okay, so this is how it is. So this CH3 and this CH2 are actually on the same plane. That's why it is called eclipsed structure. Okay, similarly, if I draw for the second group, for the second molecule, so again I will quickly draw it. So that will be CH2 and you have H here. Okay, and if you try to draw the front ones, so this is how you are going to draw. So you have CH3 this side, you have H, and you have H this side. Okay, so this is again eclipsed. But for the third one, this is a bisected structure, by the way. So this will be drawn like this. Okay, CH2, and then I have H, and here I will be having groups like this. I have H, CH3, and I have H again. So this is bisected structure. Why it is bisected? Because this CH2 group and like it's present in between of these two groups. Okay, so that's why it is called bisected structure. Okay, similarly in the fourth one, again you will get the same thing. I will just draw it here. So this is again CH2, then H, and here you will have H, H, and H. Okay, so these are our four molecules. Now we have to look upon stability. Now in alkanes, we generally say that the eclipsed structure is less stable, the staggered structures are more stable in general. Okay, but here what happens, that eclipsed structures are more stable, and the one where you have hydrogen in the same plane with this CH2 group is actually more stable than the one where you have methyl group in the same plane with CH2. The reason is hyperconjugation. Okay, so what happens, that this sigma bond between, I'm talking about this, so the sigma bond of this carbon hydrogen bond is actually in the same plane with the pi anti bond, or it can be shared with the pi anti bond of this alkene or this carbon carbon double bond. So that's why this is in hyperconjugation with this double bond, and that makes this most stable. So one thing you have to remember, that in alkenes, when we are finding out the stability of the alkenes, eclipsed ones are more stable than the bisected ones, and among the eclipsed one, where the hydrogen is in the same plane with this CH2, that is going to be most stable because of hyperconjugation. That is because the sigma bond of this or the sigma electrons of this carbon hydrogen or CH bond are in the same plane as the pi anti-bonding orbital of this C double bond. I can explain this by drawing the orbitals, but I hope that you have understood. If you want it in more detail, I'll make a separate video on it. Okay, so that means second one becomes most stable among all. Now I already told you that eclipsed ones are more stable than the bisected ones, so that's why your first one comes the second one. Okay, now among these bisected ones, you have to look upon that which is going to be most stable. See, in this molecule, in the third molecule, what happens, that there will be some type of repulsion in between of these two groups because they are quite near to each other, or they are in gauche position, right? So the third one is going to be less stable, whereas there is no such repulsion which is present in the fourth one because all are hydrogen over here. So that means the fourth molecule is more stable than the third one. So the correct order of stability follows this particular trend, which is there in option number D. Okay, so this is how the stability of alkenes is understood. I will suggest you to read about stability of propene. Okay, it's a very interesting molecule, so try to read the stability of that and how hyperconjugation takes place over there. Let's take the next question now. Alright, let's look upon this question. It says, consider the structure of the following organic compounds 1, 2 and 3, the correct relationship between HA and HB. So this is HA, this is HB for the first molecule, this is HA, this is HB for the second molecule, HA and HB for the third molecule. Now I have made a detailed video, I already told you on enantiotropic, diastereotopic, like toposity I have explained on in that particular video. I'll give you link of that in the I button. Please watch that video in detail. But here I'll just to tell you quickly that if two groups, okay, if two hydrogen are replaceable or interreplaceable by C2 axis, okay, if you can rotate them or change them by C2 axis, they are homotopic. Okay, whereas if two hydrogen can be replaced by mirror plane, okay, or you can apply a mirror plane, in that case they are enantiotopic. Okay, and if you cannot do any one of these things, in that case it is diastereotopic. So let's look upon option C because that is easiest one. You can see that if I apply a C2 axis and if I rotate it along this, these two hydrogens are going to interchange their positions. That's why these are homotopic. Okay. Now here you might think that I can apply a plane like this, alright, and I can interchange, axis like this and interchange them. But no, this molecule or this carbon is sp3 hybrid. So you cannot apply a axis like that. It is shown like this, but this carbon will be actually like this, right? It will be having methyl group CH3, let's say, and then CH2, and then CH3 like this. And one of this HA will be out of the plane, like below the plane, and one of them will be above the plane, right? This is how it will be. So these groups cannot be interchanged. You cannot apply any axis over here. So how you can like how these two things are interchangeable? By applying a plane here. So if you apply a mirror plane which passes in between of these HA and HB, if that plane passes from between of both of them, in that case they can be reflected in that plane, right? And all the other groups will remain on the plane itself. But you cannot apply axis, because if you apply axis, this ethyl group will go on the other side, this methyl substituent will go on the other side. So that's not a proper rotation. Whereas in this was a symmetric molecule, that's why it was possible. So here mirror plane is possible, that's why it is enantiotopic. Now this is how homotopic, this is enantiotopic. You got your answer. Answer is option number A. Let's verify it. So in option number 1, you cannot rotate it by any axis. There is no axis of rotation to interchange these two. There is no mirror plane as well, because if you try to apply a mirror plane, one side you have bromine and one side you have hydrogen, they are not going to get reflected by the plane directly, right? So that's, you cannot apply a plane again. So that's why it is a diastereotopic. See, I have explained it in very short. It's a detailed topic. If you guys want, I have already given the link in the I button. Please watch that video. I have discussed these things in detail over there. All right. Let's take the last question for this video and let's understand that as well. So it says, which of the following substituent present at cyclohexane has the least value of conformational free energy? Okay, that is delta Gc. Options are fluorine, chlorine, iodine and CH3. All right, so to answer this particular question, first of all you have to understand what is conformational free energy, okay, or how it is related to the, it's a thermodynamic property, because of course it's a free energy, Gibbs free energy, but let's try to understand from the organic chemistry point of view. So you have substituent over here. So remember that this conformational free energy is positive, okay, if the substituent tends to stay in equatorial position rather than axial position. Okay, Alright, so if the substituent prefers to stay in the equatorial position rather than staying in the axial position, in that case you have a positive delta GC. So a substituent which will try to stay in the equatorial position will give a better or will give higher conformational free energy value, okay, or higher delta GC value, because it's already negative. So yeah, you just have to understand like this, that if you have a substituent which will tends to remain in the equatorial position, it will give higher conformational free energy value. All right, now among these options you already know the more bulkier one will remain on the equatorial position, will tend to remain on the equatorial position, and that's why they will give more higher conformational free energy. So let me write down the order. So order of preference to equatorial position. Okay, so which one will stay in the equatorial position among all of them? So of course methyl will remain in the equatorial position for longest because it's the bulkiest one. Then comes your iodine, then comes your chlorine, and then comes your fluorine. So this is the order to stay in the equatorial position. That means that methyl will have highest, okay, so this will have a highest delta GC value or minus delta GC value, or the conformational free energy value, whereas F will have least delta minus delta GC value, right? So that means conformational free energy for fluorine will be least. Why? Because it has least tendency to stay in the equatorial position. It can stay in the axial position as well. So among all of them, if you have to compare, option number A, that is fluorine, will have the highest tendency to stay in the equatorial in the axial position, and that's why it will have least conformational free energy. So try to understand the concept and try to look upon the other substituent also and try to compare them, that how you can compare the ability of staying in the equatorial position with the conformational free energy. All right, so this is how we have done 10 questions in this particular video. It's very late in the night, I'm recording this video, and yeah, it took a lot of time to like record it, to bring all the questions. Please do consider subscribing the channel if you have not subscribed it yet. Thank you so much for watching this video, and do let me know which topic you guys want me to take in the next video, and I'll try to take it out. I'll try to make these videos, like these 10 challenging questions, twice a week. That is, I'll try to make on Sundays, like a video on Sunday and a video on Thursday. So right now I have planned like that. I might fluctuate a day or two, but not more than that. Okay, so I'll try to give you 10 challenging question series twice a week, that is for sure. And do subscribe the channel for more updated contents. And if you guys want to have any request for another video, like for the next video, please do let me know in the comment section below. You can follow us on different social media platform as well, on Facebook, Instagram, or Twitter. The handles are right front of your screen. So that's all from my side. Thank you so much for watching. See you guys in the next one. Till then, have a great day. Bye bye, take care. Hey guys, so I teach live on Unacademy Plus platform. Here I teach for the CSIR NET category, and you can follow me over here for regular classes. You can access my free classes as well as my paid classes on this particular platform. The classes which are free, you can get that under the section of special classes, whereas in order to access my paid classes, paid live classes, you have to take Unacademy Plus subscription. So do make sure that you take the Unacademy Plus subscription to access all my paid classes, which are quite organized. The whole syllabus is being completed over there, and the classes are quite regular over there. So make sure that you take Unacademy Plus subscription by using my referral code, that is N_Huda. That's it for this. Thank you so much.